Matthias Hamburg is actively volunteering at German Testing Board, GTB, and ISTQB, acting as the product owner of the ISTQB Advanced Test Analysis Syllabus and the Glossary Working Group Chair, both at ISTQB and at GTB. Born in 1953 in Cluj, Romania, he graduated with a PhD in mathematics and computer science at the University of Bonn, Germany. For over 30 years, he has worked as a consultant in the German IT industry. Since 1997, he specialized in software testing and quality assurance, with a focus on areas of test design, test management, and test process improvement. From 2006, his retirement in 2009 was working with Sogeti, Germany, in the position of a managing consultant. Ladies and gentlemen, Matthias Hamburg.
Thank you very much, Krzysztof. Hello, everybody. I'm happy to be here, and I'm really impressed by this large and very nice conference. It's my pleasure to present you a current topic, metamorphic testing. Who of you know what metamorphic testing means? Hands up. A little bit, not very many. So it's worth explaining it to you. Yes. Thank you. That was my situation as well. A couple of years ago, when I took over the position of product owner for the advanced level test analyst. And after issuing a minor update of that syllabus, I started to survey the publications to look for new test techniques, whether there are some new test techniques which came onto the practical market since the last issue of our syllabus. And I came across this metamorphic testing. So I will talk first about the underlying problem, and that's the Oracle problem in testing. Then I will explain you what metamorphic testing is with an example from my own experience as chair of the Glossary Working Group at ISTQB. And then I will show you a couple of few other experiences from practical case studies from practice. And then we'll see where does it fit into the test methodology. And then I'd be happy to hear your conclusion. So I'll ask you to give me your opinion. So let's start with the Oracle problem in testing. I hope most of you have heard of the test Oracle. So when we're testing, we're performing a dynamic testing, we're executing the tests, we feed inputs to our test object, we get actual results, we compare them with the expected results, and decide whether the test passed or failed. For this, we need some expected results. And the procedure deriving the expected results from the inputs is called the test oracle. So usually you do have a test oracle. For instance, if you migrate a legacy system to a new one, you might use the legacy system as a test oracle. But in other cases, you don't. And especially nowadays, when we move towards continuous testing and automating as much as we can become an issue, because if you generate inputs randomly, then you need an automatic procedure as a test oracle. Otherwise, you can't tell whether the test passed or failed. So it's sometimes a problem. Now, even though it's a current and very important, relevant problem for testing, it's not new. There is a classical paper by the Grande Dame of software testing, Hélène Voyouker, who in her young days published a paper in 1982, so it's already 40 years by now, about non-testable programs in the Computer Journal. So why did she call it non-testable programs? Because if you don't have a test oracle, you can't decide whether the results passed or failed, so it's non-testable. And in her paper, she enlisted 3 current solutions by that time that were known. First solution is to restrict testing to specific inputs which are easy to manage. So it's easy to predict the expected outcome. That's what I used in practice usually, and that's what you probably, or most of you, are also using. The advantage is that you don't have the oracle problem for those values, but the major disadvantage is that the specific or the tricky defects might hide behind difficult inputs, where it's hard to predict the expected results. So especially in applications like application domains like safety critical systems, this is not accepted as a reasonable solution. Safety critical systems by that time used another approach, developing several solutions. So maybe you develop 2 full-fledged versions by 2 different teams of the same problem or for the same specification, and then you compare their results. What you're doing there is you're developing a test oracle which actually should be tested again as well, but if they deliver the same results, the corresponding 2 solutions, then it's very likely that it's correct, right? So this is something, of course, better, more effective, but very expensive, right? So in safety critical problems, you can invest, but in other areas, you don't have the money to do it. And the third solution Elaine Bayuker enlisted is called today property-based testing, which became quite popular recently. She called it differently by that time. She said it's a partial oracle. When you do not have a full oracle for the expected result, but you have some properties that you can check, like the values should be, the one date should be greater than the other, or properties based on between the inputs and the expected results of the test within one test case. And interestingly enough, this approach already uses nowadays compensates for this incomplete test oracle by generating automatically lots of input data for the same high-level test case. So you execute many low-level test cases practically for the same high-level test case. It's somewhat popular, and it was known already in 1982. But in my study of the scientific papers, I came across a new one, and that's metamorphic testing. It's a new solution to the oracle problem, and it's based on consistency of several test cases. So you run different test cases, and their expected result or their actual results should satisfy some relations that you can check. So let me explain this with a known example. I'm the glossary working group chair, and I'm in charge of maintaining the glossary application, which is a database based application. The data are stored in a relational database, and the presentation layer is showing you the glossary terms. Who of you have ever used the ISTQB glossary application? Okay, not many, but a couple of you. Okay, and I'm in charge of maintaining it. So I have to maintain the terms in this database, but in addition, we also have a table with a syllabi, because the users need to know which term is used in which syllabus. For instance, if you attend a course, then we expect from the certification candidates that they can recall the definition of the keywords. So in the beginning of each chapter in the syllabus, there is a list of keywords, most important testing terms, that has to be remembered by the students. And so some glossary terms occur in the text and some are even marked as keywords. And so whenever we publish a new syllabus, I run a program called the glossary checker, which checks all the text of the syllabus and is searching for the occurrence of glossary terms and populates this table which tells you which term is used in which syllabus. Now, this program has been developed for the German testing board by two students a couple of years ago. They are gone since a long time, and I don't trust this program. So I have to test it, right? Whenever I run it, I have to test the outcome. And so now I'm starting to test it in a metamorphic testing, which means first I start out with a so-called source test case, and I search for the string test in the glossary, just a simple search, and run this search and obtain this result in that version. So we obtain 226 hits out of the 590 terms in total by that time when I ran this test, right? When the new foundation level has been published. This test case doesn't aim to detect any defects. It's just a source test case, the point of starting for metamorphic testing. Okay, so we assume this passed. We don't check it, we assume it passed. In the next step, we think about metamorphic relations between this test case and others. And I find a very interesting filter, which I can turn on, just for terms used in the new syllabus, Foundation version 3.1. So the metamorphic relation will be, if I run the program with this filter for the same text, then the result should be a subset of the previous result. Right, so let's run it, and let's find that it starts similarly. Some terms are now missing. We get 112 terms in total, and to be sure, I run a comparator between the two lists, and it confirms that this metamorphic relation actually passed. So this is really a subset of the previous subset. What we don't know is whether this list is accurate, right? So if I went into the text of the syllabus, I might find some terms that are not found by our checker and that are not appearing here, but used in the syllabus because of grammatical flexions or because of whatsoever. But the statement is that this metamorphic relation is fulfilled for this text. I can, of course, generate many inputs and then run this to be sure that it's always fulfilled. But instead of doing that, I transform our follow-up test case from the previous relation to the source test case of the next relation, because I discover that we can add filters for keywords only and for non-keywords only. And as I mentioned before, this is important for students preparing for a certification exam. And the metamorphic relation here is that these two result lists must partition the previous one. So they must be subsets, and they must not have common elements, and they must cover the whole set. Right? So this is the notion of partition. So let's run them. Let's run the first one for keywords and the second one for non-keywords, and everything looks fine. Test is, for instance, not a keyword in foundation level. Acceptance testing is a keyword, as you would expect. Accessibility testing is not, or exhaustive testing is not. But wait a minute. We got 64 keywords and 42 non-keywords. But originally, we had 112. So we're missing 6. Right? So this relation failed. And there is a bug somewhere. 6 terms are missing in the subsets. And that's where metamorphic testing ends. As a tester, I'm happy to have found a defect. Of course, as the product owner, I'm unhappy because I have to debug it. The students are gone, and I have to debug it. But I can debug it because I know the database structure, and I know that there is a table, a relational table called syllabus in, which creates the relations between the terms and the syllabi by ID, and I know that it has an attribute keyword which should have either the value 1 for keywords or 0 for non-keywords. So I search for values not in this set, 0, 1, and I find our 6 missing terms. What happened actually is that the students just counted the occurrence of a term in the sections keyword in the chapters, and we have 6 terms in this syllabus which are keywords in 2 different chapters. So these are the hits. Right, so what we learn here is that when we run a metamorphic test, then we will find that the relation fails, but that doesn't mean that one certain test case fails. It might be that the follow-up test cases failed, or one of them. In this case, it was the one counting the keywords. But it even might happen that the source test case is failing. We assume that it's not, but we are not sure. Right, so this is how metamorphic testing works. Now let's see some publications and how it evolved. So originally this method was introduced by a group of Chinese researchers from the Hong Kong University who published it in the technical reports of the Hong Kong University. I don't want to raise hands who is reading regularly the Hong Kong University technical reports. And they called it metamorphic testing to become more popular, and then they went on the roads and advertised it and at many conferences, but it took some time. It took several years until other software engineers or testers became interested in it. But now it became better known. So in 2018, a group of researchers from the Sevilla University, led by Sergio Segura, conducted a review of the publications, and they found 84 case studies published about metamorphic testing. And this diagram shows the distribution across application areas. It's not that interesting. Web services that are the largest single area, and computer graphics and embedded systems and so on. Today, after a couple of years, I would expect that artificial intelligence would be the biggest slide, but I'll come back to that later. So this survey has been published in 2020 in the IEEE Software magazine, which I hope some of you read, as opposed to the technical reports of the Hong Kong University. And a little later, the ISO issued a new version of the standard 29119, part 4, about the test techniques, and they included it already. So ISO considers this as a standard test technique, which is worth mentioning. And We didn't cover it yet in ISTQB Advanced Test Analysis because, as I said, I just issued a maintenance or minor version, but I'm keen to hear your opinion whether it's worth considering in the next version. It is, however, already mentioned in the recent artificial intelligence testing syllabus. So if someone of you have learned it, you should have heard of it. Okay, let's see a few examples of these many case studies, what they tell us. 2015, Lindvall and a group of testers from the US branch of the German Fraunhofer Institute published a case study about the NASA Data Access Toolkit. They have run the acceptance testing of this NASA Data Access Toolkit. So what is it? The test object is a high-performance query and research user interface for the huge database of telemetry data collected by NASA over all the missions. So NASA is launching flights in the space, airborne systems, and these airborne systems collect, have lots of sensors and other metrics collected, and these are transmitted over the air to the ground system and collected in the database. And if you plan for a new mission, then of course you have to study the metrics of the old systems to develop your new one. So this database, data access toolkits, or DAT, as they call it, has been developed incrementally. And the testers for acceptance testing had a big Oracle problem, because it's very important to know whether the results are accurate or not. And so the success of further missions is depending on the accuracy. So you can't tell, the database is much too large. And so they decided to go for metamorphic testing. And the metamorphic relations they used here are practically equivalents of queries. So they have a large range of ways how to state the queries. You can use different variables and different formats, and for instance dates in different formats, and basically you can generate equivalent queries in different variations and check whether the results are the same. And by this they indeed found a large number of defects. In acceptance testing, as you know, acceptance testing shouldn't find many defects, but so the system was tested already in system testing and so on. And what they emphasize in their case study is that it works perfectly well with model-based testing. So they were writing formal models of their metamorphic relations and then feed it into the model-based test generator and feed in the input data in the generator. And so they achieved what we would today call continuous testing, which is supporting the agile approach and software lifecycle. In the next year, another case study appeared by Zhu and others who are Chinese people in Asia, not in the People's Republic, who tested the search engines. So they tested the most popular search engines to find out whether they deliver reliable search results. So they tested Google, Bing, Chinese Bing, which is a specific variation of Bing for the Chinese market, and Baidu, which is used in the People's Republic of China. And the metamorphic relations were that, for instance, you run a search, then you find the first hit, the top hit, and then you restrict the search by filtering for the URL domain, like .au for Australia in this case. and then run it again and see whether the top hits from that country are again appearing. So this would be, or similarly, you restrict your search filter by the titles in the result list, or as in the previous example, change some logical combinations. And they indeed found out that none of these search engines are reliable. So what they did is they ran lots of data in this metamorphic testing for a longer period of time, because the oracle problem here is that the database is constantly changing, right? So these search engines are always crawling the internet and adding data to it, but it still has to stay consistent, and none of them were consistent. However, as you might guess, Google was doing better in English, and Baidu was doing better in Chinese. Right? They reported the defects to the providers, to the companies, because they don't have access to the source code or to the development, and the companies indeed fixed those defects. The next example, 1 year later, again, the group of Lindvall were testing the safety of autonomous drones. And here we come to the main application area, to artificial intelligence, which is nowadays in focus. So the test object is the drone artificial intelligence controller, and it wasn't about military drones, it was about transportation drones, which transport a parcel to a certain destination and have to turn back to the starting point. Here the oracle problem is whether the autonomous drone behavior is safe and as expected. So on this flight route to the destination, the drone has to avoid obstacles and fly on a safe route and land safely and depart safely and all this. So the metamorphic relations that they tested were that you start out with a certain scenery, with a destination at a certain distance to the north and a certain arrangement of obstacles, and then you might rotate it by a certain number of degrees, or you might translate it, or you might change the distance to the obstacles, or you might geometrically change the arrangement of the obstacles, right? And the routes should be similar. And let me show you one example. So they started out in the northerly direction, and they had a destination. This is the square up at the top at the right, and the three dots are three obstacles in the middle. One of them is on the direct route, and two others are on both sides arranged on a circle, right? So the question is how the drone will avoid this obstacle. And from in the northerly direction, and even if you rotate it by 25 degrees, the drone flew towards the obstacle first, then it noticed the obstacle, made a right turn, flew around the obstacle, and then landed safely, came back, and avoided the obstacle again on the same side, and came back to the starting point. But interestingly, if they rotated the scenery by 27 degrees, then the drone took the other way and flew around the obstacle to the left, and on the way back on the same side. So they started to wonder, where does it change? And they tested it, and they found an angle a little bit above 25 degrees, where the drone flew directly into the obstacle and crashed. So this is one example from their paper, and it's nice to see how they find the failures. A similar case study, and this will be I think my last case study is about autonomous driving. A group of testers, Tian and others, have published it in 2018, where they were testing the control systems for autonomous vehicles. And they took the three top performing deep neural networks. There is a thing called the Udacity Self-Driving Car Challenge. I'm not an expert in that, but it sounds like something very exigent. And so they wanted to test whether these systems are driving safely. Now, the Archer problem is here again. These are systems that did some machine learning, learned how to drive the car, and you don't know exactly how they will drive the car, but it should be safe, right? They should stay on the road and so on. The metamorphic relations that they are testing are that you have the same driving task under various environmental conditions like rain falling or fog or blurring picture or picture scale. So the camera presents a different picture scale than originally, or brightness, rotation, and so on. And they found indeed hundreds of failures. And interestingly, they introduced a framework which they call deep learning test, and they published the results on GitHub. So now one of the pictures from GitHub is, this is the source test case. You have a nice country road. You're driving along the country road towards a left curve, and you have oncoming traffic, and it behaves as expected. And then you add some rain to it, right? So rain falling on the windshield, and immediately the system is driving into the oncoming and probably causes a fatal accident. So I would really invite you to visit this page before you enter a self-driving autonomous car. Okay, so we had fun with failures, and let's now do the hard work. What is the method behind it, or the methodology? Well, usually people writing about metamorphic testing describe the process in some steps. So first you analyze the metamorphic relations, then you design source test cases and follow-up test cases, and then you design the test procedures. Combining them, as I did in the beginning, you can make a follow-up test case to the source test case of the next step, and then finally you execute your test suites. Generating, really, that's important to mention, generating lots of input data. That's the process, and out of this, the analysis, as usual, is the human and most essential creative activity, not the rest. Analysis is an essential creative activity, and you need the knowledge of the application domain. You need to know the specification and how it behaves. You need a functional decomposition to find out what are the metamorphic relations. You need skills to formally specify these relations in order to include it in a model-based testing environment, and usually you go for the highest possible code coverage, so you need also tools to measure code coverage. I'll come back to that a little bit later. And based on that, you can differentiate between two approaches. One of them is input-oriented, so you look at the input and reflect which change of the input leads to a verifiable change in the output. Or the other way around, output-oriented, when are the expected outcomes identical or a partition or equivalent, and then find the related inputs. But it's always this activity that determines the effectiveness, so how many of the existing defects you will detect. Now, a special slide for Monica. We discussed yesterday about the relationships between testing entities. Within the glossary working group, we were discussing that not only the terms, but their relationships are also very important to understand all the model. And here is our model. It's a UML model where the swim lanes are the activities of test design and test analysis, design, implementation, and execution. And in the beginning, you start out with the test basis, which is in gray because it's not a work product of testing, it's an input. And then you derive test conditions, which are aspects that you want to cover, and test cases from the test conditions. And from the test cases, you come to test procedures or test scripts, which combine test cases in a specific order to perform them, and then you combine them into test suites, which you want to execute on a certain version of the software, and then you run your tests. You have a test runs and actual results, and if you then you will have the traceability from the actual results to the test conditions. Now, applying this to metamorphic testing is very easy because the test basis is usually specification, and the test conditions are the metamorphic relations. So these are the things that will fail or pass in your testing, running your tests. But the difference is that you have two types of test cases, source and follow-up test cases. And this means that the expected results are not part of the test case itself. They are part of the combination of test case and source and follow-up test case. So they are part of the test procedure, actually. And of course, the results refer to the metamorphic relation. One important question is, when you have a test technique, what are the test end criteria? When do you stop testing? How much do you want to test? And the ISO standard states that there is currently no industry-agreed approach to calculating coverage for metamorphic testing. Because if you covered all your relations by one test case each will not be sufficient. And you don't know how many test cases to generate or how many inputs, low-level test cases to generate for the high-level test case. But in the case studies, we encountered two interesting options. One option is to test as long as the defect detection rate is good. So as long as you discover new defects by adding new input data and running the same metamorphic testing, it's worth continuing. When you don't discover any more, then you stop. And the second option was in connection with the neuron coverage. So white box coverage is also a good option. If you reach white box coverage, then the case studies prove that you reach a good defect detection effectiveness, right? So you won't detect many defects afterwards. So my conclusion is, for myself, that metamorphic testing has proven its value in practice. It's a relatively new test technique, as you've seen. It's especially suitable for test objects with a relevant Oracle problem, like web services with huge databases, so you can't really know what is accurate, what not, or like artificial intelligence, where you cannot exactly predict the behavior of the system. It learned something, and just like your kids, you don't know how it will behave in a certain situation. And it's integrating well with model-based testing, and by that with continuous testing, supporting also life cycles like Agile and DevOps. And the defect detection effectiveness has been proven by these case studies. And the efficiency is highly depending on the degree of automation. So you shouldn't start doing it like I did, just manually with the glossary. In small toy examples it works, but if you're in large projects, then automation is essential. So here is my question to you. Does metamorphic testing deserve to be included in the current, in the new syllabus, in the canon of test techniques? Should we do it or shouldn't we? What do you think?
A show of hands.
Discussion.
Who's for?
Discussion. Okay, not the vast majority.
And who's against? Maybe let's check
Against?
the other condition.
Yes. Oh, no one dares. Abstentions? No. So the rest
Who'd
is
like to abstain?
abstaining. Yes. Okay. So questions, discussion.
Thank you very much, Matthias. That was an excellent piece on metamorphic testing. A big hand for Matthias, please.
Thank you.
We have time for 1 or 2 questions before the break. I can see the first one coming from the first row.
I'd like to ask about a little bit of clarification about the input data. So my impression was that the metamorphic testing is a technique that is meant to be used by a large volume, large data sets. Would that be correct?
Yes, I agree. Yeah.
All right, thanks.
Yeah, so you need a generator, and you need, of course, a generator which generates consistent input data, not invalid ones, the ones that fit into the metamorphic relation. Yes.
Who'd like to come next?
If nobody else, then I'd like to have a second question.
Yeah.
So in this diagram, when you showed the flow of designing the tests,
Right.
you had, I think, source tests and then follow-up tests. So is it common in metamorphic testing that a follow-up test becomes a source test for another follow-up test?
Well, it's I don't know how common it is. It's mentioned always by the experts that you can do it. Right?
Okay.
So it makes sense to do it.
Thanks.
Like in case of filtering, you know, you put one filter and add another one and so on.
We could squeeze in one more. Thank you very much. Matthias, Hamburg, ladies
Thank
and
you.
gentlemen.